From the studios of Postscript Media and Canary Media.
I'm Shail Khan, and this is Catalyst.
So if you look at replacing natural gas with hydrogen, and they have the same leakage, then you get 5 times less impact from the hydrogen compared to natural gas. But you're also replacing the natural gas, which has substantial climate impact from the fact that you're burning the natural gas and it turns into CO2. So unless you capture that effectively, that's the big ticket here, not necessarily the comparison of the leakage.
Hydrogen leakage is nothing to make light of. Light? Get it? Periodic table joke? Anybody?
Let's face it, environmental news is often very depressing. That's why we focus on solutions on this podcast. But still, the climate crisis looms large. Rising temperatures, mounting pollution, environmental degradation, they're all warping the planet. And for a lot of species, including us, things don't always look so great. But the story doesn't end there. Every Friday, Living Planet, a show from Deutsche Welle, takes you behind the headlines to figure out what's happening and how we'll get through it. It'll also help you make better choices for a healthy planet and find space to reconnect with the beauty and wonder of the world around us. You can find Living Planet wherever you get your podcasts.
I'm Shail Khan. I invest in revolutionary climate technologies at Energy Impact Partners. Welcome. You know what podcasts are great for? Nuance. I mean that sincerely. Some topics just require it and are, in my humble opinion, really poorly served by other forms of media, particularly written media. Case in point is today's topic, which is the potential impact of hydrogen leakage on global warming. Many of you have written in to suggest this as a topic over the past year or so, as this issue has started to enter the collective climate tech consciousness, thanks in part to a few new academic studies and some news articles that have come out about them. This has led to some alarming headlines, or at least alarming in my circles, such as, quote, emissions of hydrogen could undermine its climate benefits, unquote. And predictably, there have been others taking the opposite view, that this is a big nothing burger. Having spent a fair bit of time on this myself, in part because I've made multiple hydrogen investments myself, I think most folks actually agree on the key point, which is that if a lot of hydrogen leaks into the atmosphere, that could have impacts on global warming, bad impacts on global warming. But how much is a lot and how bad it would be and relative to what and how worried we should actually be about it and how that impacts the highest and best uses of hydrogen, those things are all in the realm of nuance. And that nuance really matters here because it affects how we should be thinking about hydrogen as a lever for decarbonization. So I will lay my cards on the table at the start, just so you know where I'm coming from. Having read all this research and spoken to a bunch of folks about it, I still think hydrogen has a huge role to play in decarbonizing a variety of industries. Consider me a hydrogen bull. But I do think that this issue that we're going to talk about should impact, one, where we promote hydrogen, and two, how it's regulated and what we're paying attention to as we build out hydrogen infrastructure. So with my own view out of the way, let's help you build your own. And to help us do that is Thomas Koch-Blank. Thomas is a senior principal at RMI, where he leads their Global Breakthrough Technology program and has been spending a lot of time looking at these questions around hydrogen leakage and what it means for the future of decarbonization and energy. Here's Thomas. Thomas, welcome.
Thanks for having me.
Let's talk about hydrogen leakage. So I think this is an issue that deserves a lengthy conversation with a lot of nuance, but let's start with a high-level overview of the science. There have been a few papers that have come out recently, both in the US and the UK, that have raised alarm bells to some degree regarding the possibility that hydrogen leakage into the atmosphere could have a negative impact on climate change, have a warming effect on the planet. Can you just walk us through what that mechanism might be? Why would that be true?
I will give it my best shot, acknowledging that I am not a scientist on this topic myself, but I've done my best to read up on published research and try to understand what it means. But I think the bottom line conclusion is that hydrogen seems to have a higher global warming impact than what we previously thought. If you go back in the tables that have been developed by the IPCC process and used in all the national inventories for hydrogen leakage, the number has been significantly lower than some of the recent research suggests. And there are a couple of things happening here, and mostly it's to my understanding, the secondary or indirect effect that has been neglected previously. So basically what happens is that the hydrogen that leaks has itself a global warming potential, which has been considered, but then also it has an effect of extending the lifetime of methane in the atmosphere, basically causing the methane to stick around longer, and that has obvious effects on the greenhouse, sort of the global warming impact of that methane. And then I think that there is also some interaction with the ozone layer that has, as a consequence, that the hydrogen creates stratospheric water vapor, which has another indirect effect on global warming.
So one thing I think is important to clarify here at the beginning is that we're talking about hydrogen that is leaked into the atmosphere as opposed to hydrogen that is burned or consumed in a fuel cell, right? We're not talking about if you burn hydrogen, for example, or if you consume it in a fuel cell, whatever you do with it, that doesn't then leak into the atmosphere, create this indirect effect on methane. So this is hydrogen that leaks as hydrogen gas or as hydrogen directly into the atmosphere, right?
That is accurate. And that, from that perspective, it is quite analogous to the whole discussion around methane leakages from natural gas supply chains that has a sort of indirect effect on, or if you like, undermines the carbon emission reductions that are achieved by switching from coal to gas, for example.
Right. Though there is one key distinction there, which is that because natural gas has carbon in it, if you burn it, it turns into CO2, and you do still have CO2 released into the atmosphere. If you leak it, it's CH4, and that's methane, and that's bad. It's worse, but if you burn it, you still have CO2. With hydrogen, if you burn it, you're just burning hydrogen. There's no carbon in there. But if you leak it, it turns out, it looks like there is this indirect effect on methane lifetime in the atmosphere and on the ozone layer. Now, this science there have been multiple papers on this. As you said, it's sort of what it's coming up with at the moment is different from what has been assumed in the IPCC and other places historically. So what is your sense of where we are in the science here? How certain are we of this basic principle? How much precision do we have around it, or are we just sort of at the very beginnings of understanding this?
I think we can. My understanding is that we can credibly say that the global warming potential or impact from hydrogen is higher than we previously thought. I think the exact number is going to move around a bit because we're learning about this indirect effect.
So could you just walk me through then what we think the global warming potential of hydrogen, if it leaks into the atmosphere, might be, and maybe contextualize that against things like methane, just so that we have a frame of reference here?
Sure. And I think there is a fairly straightforward answer here, but it also becomes a little bit contingent on assumptions or, starting point. So what research has found is that the global warming potential, which has been traditionally considered, has been, I think, 5 kilograms of CO2 equivalent per kilogram of hydrogen leaked. And the recent research indicates that it should rather be 10. Now, I think here's where the framing picks up, because that is a well-supported conclusion. But then there are a couple of things to keep in mind. One is that, the energy content in hydrogen is much higher than the energy content for methane. So for each kilogram of hydrogen, you'll have 120 megajoules, but for each kilogram of methane, you'll only have 50. So if you're trying to replace natural gas with hydrogen, the relevant comparison is not on a per kilogram basis, but on a per megajoule basis, right? So that needs to be taken into account when you start benchmarking. And the second is, and that's also, this is an area where it's outside of my area of expertise, but it seems to be an area where more research is needed, which is what kind of an equivalency should you use for hydrogen? So basically, as a reference, we talk about 100-year equivalency and 20-year equivalency for translating the global warming impact of a gas to carbon dioxide, right? For methane, or I would say fundamentally, since the establishment of the Kyoto Protocol, we have based most of our inventory and policy on 100-year equivalency. Lately, there has been a strong push to shift towards a 20-year equivalency for methane because of the near-term impact. I think some of the research on hydrogen is suggesting even shorter timeframes for hydrogen, some of them down to a 2 or 5 or even 2-year equivalency for hydrogen compared to CO2. And here, I think more work is needed to understand exactly what makes sense and why.
Okay, so just so that we have, one of the takeaways here is that there's a lot of nuance to these numbers, and it's important not to just take a single number at face value because it's dependent on all these different assumptions. It's not all perfectly normalized and so on. So there's nuance here that's just inherent to how we think about this stuff. But just for a frame of reference, let's say we're taking a 20-year global warming potential, so nearer term than the 100 years that, has been sort of de facto standard historically. But we're also normalizing hydrogen and methane for their energy content. Just where do they stack up against each other from what we know in terms of global warming potential?
So, first of all, just on a per kilogram of gas comparison, when you look at hydrogen on the 100-year equivalence basis, you're looking at a global warming potential of 10. But if you go similar to methane, when you go on a shorter lifetime here, you will have a higher number. So for natural gas, it goes from 25 to 80 roughly when you compare 100 to 25. And for hydrogen, it goes from 10 to 40. So it increases substantially, but it's still half of the global warming potential of natural gas per kilogram. But then hydrogen has a higher energy content of almost or roughly 120 megajoules per kilogram, and natural gas is around 50. So there is a factor of 2.5 again. So the first factor of 2 and then another factor of 2.5 gives you a total factor of 5 in between.
Okay, so in other words, roughly speaking, if we're thinking on a 20-year basis, if you leaked 1 kilogram of if you leaked 1 megajoules worth of hydrogen into the atmosphere and 1 megajoules worth of natural gas into the atmosphere, we think the natural gas would have roughly a 6 times greater impact on global warming than the hydrogen would.
Right, or
over a 20-year period, adding all of my of my nuances.
So look, and that's so if you look at replacing natural gas with hydrogen, and they have the same leakage, then you get 5 times less impact from the hydrogen compared to natural gas. But you're also replacing the natural gas, which has substantial climate impact from the fact that you're burning the natural gas and it turns into CO2. So unless you capture that effectively, you have, that's the big ticket here, not necessarily the comparison of the leakage, even though both are relevant.
Okay, and then let's talk about these studies that have found this, because I think the studies themselves have been, at least from what I can tell, well considered and come up with valuable evidence to add to this line of questioning. Some of the headlines about the studies have been scary, and I think a lot of it comes down to the assumptions in those studies, which are pretty variable, and what that implies in terms of how big a deal it would be if we scale up hydrogen within our economy. So can you just talk a little bit at the high level about sort of what are we assuming in these studies and how does that impact what the results would be?
Well, I think you can look at the transition in a few different ways, and you can either have as a starting point assumption that everything goes wrong, or you can have a starting point assumption that we will broadly figure things out. And I think that starting point makes a difference, and whether you're sort of looking for the unintended consequences that we need to avoid, or whether you're looking for the good solutions that we want to promote, right? And that has some bearing on what assumptions you make, I think. And I haven't seen all the research that you're referring to, but I think some of the papers I have seen seem to assume very large adoption rates for hydrogen in the economy, for example, which I think many of us who work with hydrogen a lot would consider to be a big number, which is unlikely as an outcome. But then again, if you do assume such a scenario and you apply very big global warming potential to those, that consumption with a reasonably high leakage rate, then the conclusion gives you, the fact base for a big headline, right?
Yeah, I mean, I think there are at least three vectors that are worth teasing out individually. The first is how much hydrogen do we just end up using, as you said, right? And, some of these studies sort of take this maximal possibility of like, let's just say we replaced 50% of natural gas in the world today with hydrogen in the future. And that obviously results in hydrogen being a huge part of the global energy economy. And indeed, maybe that happens someday, but that assumes.
But I even saw one of these papers suggesting, or as a endpoint in their estimate, suggesting that 100% of total final energy consumption would be hydrogen, which again is an even bigger number.
Okay, right. So one question is just how much hydrogen do we use in general, and the more we use, almost inherently, the more is ultimately going to leak. And so, depending on how bad that leakage is from a global warming perspective, that could be a challenge. The second is where we use it, what we use it for, right? And I think this is one thing where, as far as I can tell, kind of everybody who's like engaged in this discussion around this research tends to agree, I think, which is one thing, if you just take as a prior that hydrogen leakage is bad, then you want to leak as little as possible, and you want to prioritize the use cases that need hydrogen the most, or where hydrogen provides the best possible solution to decarbonization relative to everything else. And for both of those reasons, it seems to me that generally everybody then takes one step further and says, okay, probably if we're prioritizing use cases for hydrogen, we should, for example, prioritize large industrial use cases over the distribution system, over replacing home heating with hydrogen through a hydrogen distribution system, because we're more likely to have more leakage in that system and because there are credible alternatives there. Whereas heavy industry, fewer credible alternatives, less pipes that could be leaky pipes, less likely to have as much leakage. First of all, do you think that I'm coming up with the right conclusion there? And do you think that is generally agreed upon, or is that still up for debate?
That was a long and leading question, I guess. But I would argue the same, with the only slight difference that in that conclusion, I don't think the leakage is sort of the dominating criteria. Because, yes, we want to avoid leakage, but there are other reasons to prioritize hydrogen use in the sectors where we have, not very many other alternatives, or where direct electrification is not easily implemented, from fundamental economics and from the fact that I think that in this transition, the renewable energy supply will be one of our biggest sort of system level bottlenecks, and we want to get the most out of each electron we get out of our wind turbines and solar farms. So from that perspective as well, you want to use those directly as much as you can, instead of transforming it to hydrogen, and then potentially transforming it again. So I think for me, the rationale is fundamentally from, basic energy efficiency, and then secondly, from a business perspective of where you get the most bang for the buck, if you like. And then that happens to correlate quite well with where we're likely to have less leakage. So that's what I mean. I think we have very similar conclusions in terms of priorities and implications of the findings of this new research. It hasn't honestly changed our view much in terms of priorities and how to build up a hydrogen economy. It just happens to strengthen the priorities we had.
And then the third vector, I think, is just the leakage rate itself, how much hydrogen actually does leak, which obviously has a huge impact on the impact of said leakage on warming. Now, I've seen in the studies anything from low leakage rates, 1 or 2%, up to what seem to be really high leakage rates, like 10%. How much do we know about likely hydrogen leakage rates? Should we be concerned about 10% plus leakage and the implications that that would carry? Is this just a call to arms for regulation to do sort of at the front end what we didn't do at the front end with methane? Or how do you think about the leakage rate?
So it's partly true that we don't know because these systems have not been built out. And it's also true that if we build them out poorly, we will have a lot of leakage. Now, I guess the big question here is, what are the drivers or rationales for industry to build a very tight system, which will have some marginal capital expenditure involved, right? I think there are a couple of things that are speaking to... Sorry, let me put it this way. I think it's natural here to compare to natural gas systems, because that's a gas transportation system or distribution system that we have implemented at scale. The natural gas system is arguably leaking quite a bit, and there are reasons to believe that hydrogen will leak more, mostly from fundamentals of the size of the molecule and the properties thereof. But there are also reasons for these systems to be less leaky. And I think one of the reasons that, and I'm stepping out here of sort of foundational science and peer-reviewed research, right? And but I think one of the rationales that I can relate to, having been working in industry for quite some time, is the safety aspects of leaking hydrogen, because the properties of leaking hydrogen is much more dangerous than leaking methane, partly because it's harder to detect. So that's one reason why systems are likely to be tighter. I think also there are some, on the margins, some reasons driven by economics of the value of the gas being higher. So it's likely to be worth investing that marginal capex in making sure you don't leak your valuable product. But then again, that can arguably made a case for natural gas as well, but still we see a lot of leakages. So I'm not sure I want to bank the future of the planet on sort of vague references to techno-economics here.
So stepping back then, I think the core question that comes out of this research is, well, look, the one thing we know we don't want to do is expend all this time and effort and money replacing one fuel, in this case largely natural gas, which we need to replace predominantly because of its climate impacts, not because we're running out of it necessarily, with another fuel or another gas, in this case hydrogen, only to discover that it was a wash or close to a wash from a climate perspective because of these indirect impacts that we're discovering. Can you just summarize your views on that? Is that a real risk? Or should we be thinking about this more as, look, we've uncovered something we need to keep a watchful eye on as we scale hydrogen up, because we want it to have the maximal benefit, but it's not really a concern that it could overshadow the benefit by leaking.
So to some extent, both. But I'll say that, high performing hydrogen is undoubtedly having a net positive impact on climate emissions. And by positive, I mean lower, not higher, right? I think there are many ways that we can end up with hydrogen supply chains that are having, marginal or limited impact on the global warming. Leaking is not the major issue in my mind. Leaking of hydrogen can contribute on the margin, but the big issues are things like making sure that we implement diligent regulations on blue hydrogen to make sure that we have high capture rates and still have a natural gas supply chain with limited leakages, because the leakage of methane from natural gas will be, order of magnitude higher impact than the leakage of the final hydrogen product, right? And of course, to take another extreme example, we don't want to make hydrogen with electrolyzers using coal power. We want to make sure that, or gas power by all means, right? So we want to make sure that we have rigid supply chains in how we make the hydrogen. And then, on the margin, if you include the leakage, you'll have to have a slightly tighter threshold still. But it's, again, it's not irrelevant, but it's not the major big ticket item for hydrogen supply chains.
Yeah, if I can just summarize what you just said, or attempt to summarize, because this has been my primary conclusion as well, which is the most important thing in transitioning to hydrogen, whatever sector we're talking about, is the embodied emissions of the hydrogen production itself, because that is a real challenge. Transitioning to hydrogen does not inherently mean it is lower emissions overall. It depends where that hydrogen comes from. As you said, if it's blue hydrogen, it comes from natural gas and steam methane reforming, then there's questions of upstream leakage of methane and of carbon capture. If it comes from quote unquote green hydrogen, then it's a question of where the grid electricity comes from the electrolyzer. So that stuff, when you do the math on the potential global warming impact of having hydrogen whose embodied emissions are high, relative to the potential of, I think, a realistic leakage rate and that impact on emissions, as you said, the much bigger deal is the emissions in the production of hydrogen. So our focus should be on that. And if we solve that, then, in other words, if we have hydrogen that is very low to zero embodied emissions, then even with a reasonable leakage rate, it's not perfect. It's not, no climate impact because of the reasons we've described. It is, however, much, 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 much better from a climate perspective than just burning natural gas, for example. I think one study said something like 75% better in a negative case. And if it's truly low emissions embodied hydrogen plus low leakage rate, then it can be 90% plus.
Right. And I think that summarizes it well. I would say, to your point, number one, make sure that the embedded greenhouse gas emissions of the hydrogen is as low as possible. I think we should. I'm in full support of regulations that ensure limited leakages. Right. I also think we should avoid subsidizing or overly supporting use cases which are not the best use of the hydrogen. And I would finally say that we should also keep track of what we do with the hydrogen, not only from a use case, but especially when we start getting into the space of synthetic fuels. It becomes a little bit more complicated again, but there are some use cases of hydrogen that are arguably not great, or even a step back in just for the sake, from the perspective of the ultimate impact. I mean, the what might sound like a ridiculous example, which I think unfortunately there might be some risk for on the margin, is taking blue hydrogen, which is effectively splicing up methane into CO2 and hydrogen, and then you call that captured CO2 and clean hydrogen, and then you recombine it into a synfuel, which is basically taking those components back and combining them into something which is branded as a clean fuel, and then you have achieved nothing except spending money and energy on converting molecules from back to itself. And I think those outliers, though, I think will be called out and sort of managed by the economy and the supply chains over time. There is a balance here to strike as well, I think, between trying to not make perfect the enemy of good. That doesn't mean that I'm suggesting we should let anything go here. Quite the opposite. But I often relate to probably the most robust governance system we have ever implemented in humanity, which is our economic reporting system. And we've been working on that for 400 years or so, plus minus, and we still have fraud, and we will still have fraud 400 years from now, because there will be participants in the economy that have malicious intent or fraudulent intent. And I think we will have outliers in the supply chains of any climate solution that will try to work the system. And we want to catch those and call them out and sort of weed them out. But that's quite different from assuming or believing that the whole economy will be a failure.
So as we think about building out hydrogen infrastructure for the use cases where we think it does make sense, then how do you think about transportation? Are we going to be building out hydrogen pipelines, transmission pipelines, maybe even distribution pipelines, depending on the use cases? And, what are the lessons that we need to take to minimize leakage, knowing that that's something we care about in this context?
So again, I think it's relevant to think about the fundamental priorities here of number one, let's use the hydrogen where we have the biggest impact. And by a wide margin, a factor of 2, that means we should use hydrogen for steelmaking. So using the hydrogen molecule for reducing iron ore has twice as much impact on the alternative compared to the alternative if you benchmark with using it for transportation applications. And I bucket here shipping, aviation, and trucking. Roughly, you get the same impact from using hydrogen in these 3 sectors because fundamentally it's the same physics, right? You're replacing an internal combustion engine running on hydrocarbons, moving something through inertia and or friction, and you're replacing it with a fuel cell with using hydrogen, and you're doing roughly the same thing, and then you have the thermal application of burning hydrogen for heat, replacing either natural gas or coal or other heat sources, and that has yet another factor of 2, roughly less impact. So from that perspective, we should use hydrogen for steel. Now, secondly, I think, again, what we're trying to achieve, at least in terms of building an economy or an industry at scale, the increments of demand is also relevant. And you need roughly, 100,000 fuel cell buses to equate to a single steel mill. And shipping is somewhere in between, with roughly 30 ships for equating to a steel mill, and those ships are all got to call at the same port. So the port is going to be another critical piece of convergence, if you like, of high demand and a single point of delivery for hydrogen. So when you start unpacking the use cases, you'll see that there are a couple of them that are high climate impact, arguably less green premium, or even, a pathway towards cost parity, and they're stationary. So all those stars are aligning towards where you want to put this. And then the big question is really here, where do you then put the electrolyzers? Are you able to co-locate them with this big demand, or are you not going to be able to co-locate them? And I will not claim to have the answer here because there are a lot of moving parts, and it's for us a big area of research in terms of basically what do you move, right? Do you move the electrons from the low cost renewable opportunities, or do you co-locate the electrolyzer with those renewable assets and you move the hydrogen in a pipeline? Or do you compromise on renewable cost and put it close to your demand? And that's not an easy question, or at least not a question that has a general single answer. It's going to be depending on the specifics of your supply chain. It's worth noting, though, that moving molecules in a pipeline is really cheap. That's what we see in other markets. There is a reason we're moving molecules to the regional power markets and then not moving electrons over copper between Europe and North America, for example. It's because it's cheaper to move the molecule.
You mentioned earlier that hydrogen is sort of difficult to identify, which is one of the reasons that there will be particular incentive to avoid leaky systems anyway for safety reasons. In the natural gas context, obviously, there's been this big whole industry built up around natural gas leakage monitoring and identification. There are sensors, there's satellite imagery, there's hyperspectral, there's all sorts of stuff. Do you think that we're going to see the same thing pop up in hydrogen world, or will it be different given both the nature of the market and the use cases and also given the different nature of what it takes to identify hydrogen?
Good question. So first of all, when I said it was difficult to detect, I think I was referring to the visual, the opportunity of visually detecting it, because it's harder to see with your eye, right? There are other properties of leaking hydrogen that makes it easier to detect. I think the flame temperature is higher. You can detect that with an infrared camera or what other types of detectors and whatnot, right? I think by the scaling of the industry, you will see scaling of detection equipment, just growing with the industry. There's a lack of statistics, I think, from the existing hydrogen supply chains. There are several pipelines in operation, for example, and they're not publicly disclosing their leakage rates or how they detect or measure. And that, I think, is that's a shame. That would be helpful for this debate, to be honest, to know what the current systems are operating at, and that could probably address some of the concerns, hopefully, or at least give some actual measured data from what the hydrogen supply chains can deliver at, right? But yeah, I think we'll see a lot of activities in that sense, and when you get to the software layer of aggregating all these measurements into a digestible sort of format, and I would anticipate to start linking these data sets to other leakage data sets and start overlapping them and linking them to agents and sort of serve as a basis for both regulators to implement policy and also, by all means, new business models that will likely emerge.
Thomas, really appreciate the time. This has been, I think, hopefully clarifying. But if not, then we'll have you back on. We'll try to do it again. I suspect that won't be necessary, though. So thank you.
Thanks for having me.
Thomas Koch-Blank is a senior principal at RMI, where he leads the Global Breakthrough Technology Program. As always, send us your questions. It was actually a bevy of questions from all of you about hydrogen that led to this episode. So keep them coming. Tell us what else we should talk about. You could also leave us a voicemail at 919-808-5832, 919-808-5832. Some people, for whatever reason, still leave voicemails. Or you can email us at catalyst@postscriptaudio.com. You can also tag us on Twitter if you'd like to find us there. If you like the show today, go over to Spotify or Apple Podcasts and leave us a rating and review. This show is a co-production of Postscript Media and Canary Media. You can head over to canarymedia.com for links to today's topics and the papers that we were talking about on hydrogen leakage. As always, Postscript is supported by Prelude Ventures, a venture capital firm that partners with entrepreneurs to address climate change across a range of sectors, including advanced energy, food and ag, transportation and logistics, advanced materials and manufacturing, and advanced computing. This episode was produced by Daniel Waldorf, mixing by Roy Campanella and Sean Marquand, theme song by Sean Marquand. I'm Shayle Khan, and this is Catalyst.